If you walk into a room at night and flip the light switch off, it feels like darkness rushes in. One moment the walls are clear, the furniture is visible, the air itself seems full of presence. The next moment everything collapses into shadow. Our intuition tells a simple story. Light left, and darkness arrived. But something strange is hiding inside that feeling. Because darkness never actually travels into the room at all. Nothing moves. No wave sweeps through the air. No invisible substance flows from the corners toward your eyes. What really changes is much quieter. Light simply stops arriving. And once you see that clearly, something remarkable begins to unfold. Because if darkness never travels, and light does, then what we call darkness is really just the map of where light has not yet reached. If you enjoy quiet explorations like this, you're always welcome to stay for the journey. And now, let's begin with something simple. Picture a small lamp sitting on a table. When the lamp is on, light spreads through the room, it reflects from the walls, the floor, the ceiling, and everything in between. Millions upon millions of tiny particles of light, photons, leave the bulb every second and scatter in all directions. Your eyes collect a tiny portion of them. That is what vision really is. Not objects sending information to your brain, but photons bouncing through space and landing on the delicate sensors in the back of your eyes. We rarely think about it this way, but a lit room is actually full of motion, invisible motion. Light is constantly crossing the space around you, like rain falling through the air. Now imagine that rain suddenly stopping. Not reversing, not flowing backward, simply stopping. The drops already in the air keep falling until they reach the ground, but new drops no longer appear above you. That is almost exactly what happens when you turn off a light. The bulb stops producing new photons, but the photons that already left the bulb a fraction of a second earlier continue travelling until they hit something. Perhaps a wall, perhaps the carpet, perhaps your eyes. And they are moving astonishingly fast. Light travels through empty space at nearly 300,000 kilometers per second. That is fast enough to circle the entire Earth more than 7 times in a single second. Inside a small room, the distance between objects is tiny compared to that speed. A photon can cross a living room in less than a billionth of a second. So when the lamp switches off, the last photons already in flight finish their journey almost instantly. Your eyes receive the final few arrivals. Then nothing else comes. That moment, the moment when photons stop reaching your eyes, is what we call darkness. But notice what did not happen. Darkness did not travel across the room. It did not pour in from the corners. It did not sweep across the floor. Instead, the rain of light simply ended. This may sound like a small difference, but it begins to shift something deeper in how we imagine the world. Because if darkness is not a thing that moves, then the only thing that truly travels is light. And that means every time we think we're seeing darkness move, we're actually watching something else entirely. Consider a shadow on the wall. Perhaps you've noticed this at sunset. A tree outside your window casts a long shadow that slowly stretches across the room. As the sun moves lower in the sky, the shadow slides across the wall, the floor, the furniture. It looks like a dark shape crawling across the surface. But again, darkness is not actually travelling across that wall. What's really happening is that sunlight is arriving from a slightly different angle each moment as Earth rotates. Where the sunlight reaches the wall becomes bright. Where the tree blocks the sunlight, photons cannot reach the wall. That region remains darker. The shadow is simply the region where light fails to arrive. And as the angle of incoming light changes, that region moves. In other words, the shadow is not a thing sliding across the wall. It is the shifting boundary between where photons arrive and where they do not. Once you see it this way, something surprising becomes possible. A shadow can appear to move faster than light. At first, that sounds impossible. After all, we just said light has a speed limit. Nothing with mass or information can outrun it. But the edge of a shadow is not a physical object. It carries no matter. It carries no signal by itself. It is simply a boundary defined by geometry. Imagine a lighthouse standing at the edge of the sea at night. Its beam slowly rotates, sweeping across the water. Close to the lighthouse, the beam moves gently across the surface. But far away, perhaps dozens of kilometers out at sea, the same beam covers enormous distances in a short time. The spot of light racing across distant waves could easily move faster than any ship. And if the distance were large enough, the spot itself could sweep across the ocean faster than light travels. Yet no law of physics is broken, because nothing physical is actually moving that fast. The beam consists of photons travelling outward from the lighthouse. Those photons still move at the speed of light. The fast-moving spot on the ocean is simply where different photons arrive. A shadow works the same way. The darkness itself is not travelling. It is only marking the absence of light as conditions change. And once we recognise that, the question in the title begins to dissolve. If light has a speed, what about darkness? Darkness has no speed. It cannot move because it is not a thing. It is a condition, a region where photons have not arrived. But this simple realization opens a door to something much larger, because once we stop imagining darkness as something flowing through space, we begin to notice that almost everything we see in the universe is defined by the journeys of light. And those journeys take time. Let's leave the room for a moment and step outside. When the sun sets, the sky gradually darkens. The colours fade from blue to orange to deep violet. Eventually the stars appear. It feels like night slowly spreads across the landscape. But again, night is not travelling across Earth like a wave of darkness. What is actually happening is far more beautiful. Our planet is turning. Earth rotates once every 24 hours. At the equator, the surface moves at roughly 1,600 kilometers per hour. That is about the speed of a fast airplane. As Earth spins, the side facing the sun receives sunlight. The opposite side faces away and receives none. Between them lies a moving boundary, a thin line where day becomes night. From space, this boundary is called the terminator. It slowly sweeps across the planet as Earth rotates. Cities pass through it one by one. Mountains fade into shadow. Oceans shift from bright blue to deep black. To someone standing on the surface, it feels like darkness is arriving. But what is really happening is much simpler. Sunlight is no longer reaching that location. The flow of photons from the sun is being blocked by the curve of the Earth itself. And here another quiet fact enters the story. The sunlight that illuminates Earth does not arrive instantly. It takes time to get here. The sun is about 150 million kilometers away. Light crossing that distance needs a little more than 8 minutes. That means the sunlight warming your skin right now left the sun 8 minutes ago. If the sun were to vanish, hypothetically, Earth would continue receiving sunlight for those 8 minutes before anything changed. For 8 minutes, nothing would look different. Birds would still fly through the sky. Cars would still move along highways. Ocean waves would still roll toward the shore. Because the photons already on their way would continue their journey. And only after the final ones passed would darkness appear. Not because darkness travelled from the sun to Earth, but because the rain of light finally stopped. And once we realise this, the scale of the idea begins to grow. Because the same principle applies not just to lamps and sunsets. It applies to the entire universe. Every star we see in the night sky is sending photons across unimaginable distances. Some of those photons travel for years before reaching us. Others travel for centuries. Others for millions or even billions of years. When you look at a star tonight, the light entering your eyes is ancient. It began its journey long before your life began. In many cases, before human civilization existed at all, the star you see is not the star as it is now. It is the star as it was when the photons left. And everything beyond that star, every region whose light has not yet reached us, remains dark to our eyes. Not because darkness fills it, but because its light is still on the way. So when we look up into the night sky, what we are really seeing is a kind of history written in light. Each point of brightness is not simply a distant object glowing in the present moment. It is a message that has been travelling through space for a very long time. A photon leaving a star begins a journey across enormous darkness, and only at the end of that journey does it become visible to us. In that sense, the night sky is less like a photograph and more like a slow delivery of ancient letters. Some of those letters are relatively fresh. The light from our nearest stellar neighbour, Proxima Centauri, travels a little more than 4 years before reaching Earth. When you see that faint red star through a telescope, the photons entering your eyes left that star when 4 winters and 4 summers still lay ahead of us. Other letters are far older. The bright star Vega, one of the most recognizable lights in the northern sky, is about 25 light-years away. The light arriving tonight began its journey when many of the technologies we now take for granted had not yet been invented. And then there are stars whose light left before recorded history. Some of the faint points you see in the darkness began their journey hundreds of years ago, long before electricity lit our cities, long before the first telescopes revealed the structure of the heavens. That realization slowly shifts something in the way we think about darkness. Because what we are really looking at when we stare into space is not a solid blanket of blackness punctured by stars. Instead, we are seeing scattered islands of light floating in an enormous ocean where photons have not yet arrived. Between those islands lies the quiet background we call darkness. But again, that darkness is not a substance filling the gaps. It is simply the absence of arriving light. To understand how vast that absence can be, it helps to imagine leaving Earth entirely. Picture a spacecraft drifting far beyond the atmosphere, out where the sky is no longer blue but deep black. The sun still shines brightly in one direction, but in every other direction the universe opens outward. From that vantage point, you begin to see something remarkable. Even though space feels empty, light is still moving everywhere. Photons stream outward from the sun in every direction, expanding into space like an ever-growing sphere. Each second, a new shell of sunlight spreads farther from the star. After 8 minutes, that shell reaches Earth. After 5 hours, it crosses the orbit of Pluto. After a year, it has travelled nearly 10 trillion kilometres. And it keeps going. The light leaving the sun today will continue outward for thousands of years, drifting through the darkness between stars. Eventually, some of those photons will pass near distant systems we will never see. Others will wander through empty interstellar space without touching anything for millions of years. In most directions, they will simply continue travelling until the expansion of the universe slowly stretches their energy thinner and thinner. But the important point is this: the light is always moving outward. Darkness is not pushing back. There is no tide of blackness flowing toward the sun. There are only photons moving through an immense volume of space. And once you begin to imagine light this way, as an endless outward rain of particles, it becomes easier to understand why the universe looks the way it does. Consider the space between stars. Our galaxy alone contains hundreds of billions of stars. That sounds crowded, almost overwhelming. Yet the distances between them are enormous. If our sun were shrunk down to the size of a small marble, the nearest star would be several kilometers away. Between those two marbles would be mostly empty space. That emptiness means photons leaving one star usually travel for years before encountering anything at all. They pass through regions where there are almost no atoms to scatter them, almost no dust to reflect them, almost nothing to interrupt their motion. And when photons pass through such regions without interacting with anything, those regions appear dark. Not because darkness exists there, but because nothing is sending light toward us from that direction. It's a subtle difference, but it explains why space can be both full of light and still look overwhelmingly black. Light is moving through it constantly. We simply see only the tiny fraction that happens to intersect our eyes. Imagine standing in a vast field during a light rain. Drops are falling everywhere, but your skin feels only the few that happen to land directly on you. If you judge the rain only by what you felt on your hands, you might think it was barely raining at all. Space is similar. Photons are constantly crossing enormous distances, but the chance that one from a distant galaxy will land precisely in your eye at the exact moment you are looking up is extremely small. That is why even the most powerful telescopes reveal only a sprinkling of light across a vast background of black. But the story becomes even more fascinating when we zoom out further, because there is a deeper reason the universe contains so much darkness. And that reason is time. The universe has not existed forever in its present form. Modern cosmology tells us that everything we see began expanding about 13.8 billion years ago. At the very beginning, the universe was hot and dense. Light could not travel freely because matter was packed so tightly that photons scattered constantly, like headlights trying to shine through thick fog. Only after about 380,000 years did things cool enough for light to move freely across space. When that happened, the universe filled with radiation streaming outward in every direction. Some of that ancient light is still traveling today. In fact, it is still passing through your body right now. Astronomers call it the cosmic microwave background. It is the faint afterglow of the early universe itself, stretched and cooled by billions of years of expansion. Sensitive instruments can detect it coming from every direction in the sky, which means even the darkest region of space is not perfectly dark. Ancient photons from the birth of the cosmos are still quietly crossing the universe. Yet even with that glow, most of the universe appears black to our eyes. And the reason brings us back to the speed of light. Because light travels incredibly fast, but it does not travel infinitely fast. It takes time to cross space. And that simple fact creates a kind of horizon around us. Imagine a bubble centered on Earth. The radius of that bubble is determined by how far light could have traveled since the beginning of the universe. Anything inside that bubble has had enough time for its light to reach us. Anything beyond it has not. Those distant regions may contain galaxies, stars, and enormous structures, but their light is still on its way. From our perspective, they remain invisible. Not because darkness fills them, but because their photons have not yet arrived. This boundary is called the observable universe. It is not the edge of reality. It is simply the edge of what light has had time to show us. And once you understand that, the meaning of darkness shifts again. Darkness becomes less like a curtain covering space and more like a reminder of distance. Every dark region in the sky is a direction where photons have not yet reached us, or where none are being sent our way. Which means every star you see is the result of a successful journey. A photon leaving a distant star survived collisions with dust, avoided being absorbed by gas, crossed unimaginable distances, and finally entered the small opening of your pupil. Your eye received it. Your brain interpreted it. And for a moment, that ancient journey became part of your experience. But even this picture still leaves one mystery unresolved. Because sometimes we see darkness behave in ways that seem almost physical. In particular, there are places in the universe where darkness appears to have a shape. And nowhere is that more striking than around one of the strangest objects we know. One of the most striking examples of shaped darkness appears near something that does not emit light at all. A black hole. When astronomers first predicted black holes, they imagined regions of space where gravity becomes so strong that nothing, not even light, can escape once it crosses a certain boundary. That boundary is called the event horizon. Inside it, every path leads inward. Outside it, light can still escape if it moves in the right direction. But here is the interesting part. Even though black holes themselves emit no light, we can still see their presence. Not because darkness spreads outward from them, but because of the way they affect the light around them. Imagine placing a perfectly dark sphere in the middle of a brightly lit fog. You would not see the sphere glowing. Instead, you would see a circular region where the fog behind it disappears from view. The object blocks the light coming from behind it. Black holes create something similar, but far more dramatic. Near a black hole, gravity bends the paths of photons. Light that would normally travel in a straight line instead curves as it passes through the intense gravitational field. Some photons curve around the black hole and escape again. Others spiral inward and vanish past the event horizon. From a distance, what we observe is a dark circular region surrounded by distorted rings of light. This is sometimes called the shadow of a black hole. But again, the darkness itself is not moving outward. The black hole is not releasing darkness into space. Instead, it is preventing light from escaping. The region appears dark simply because photons that enter it never return. A remarkable image captured by a network of radio telescopes in 2019 showed this effect directly for the first time. At the center of a distant galaxy, astronomers observed a glowing ring of hot gas swirling around a black hole. Inside that ring was a dark circle. Not a physical object we could see, a boundary defined by missing light. It is another reminder that what we call darkness is always defined by the behavior of photons. If photons arrive, we see brightness. If they do not arrive, we see darkness. Nothing needs to move for that change to happen. And yet, in everyday life, the illusion that darkness travels remains incredibly strong. Consider once more the moment when a shadow sweeps across the ground during sunset. The motion feels real. The dark edge slides steadily across grass, pavement, buildings. It looks like a moving object. But if we could zoom in close enough, we would see something very different. Sunlight is arriving at the ground from a slightly shifting angle as Earth rotates. Where the sunlight reaches the surface, photons scatter and reflect into our eyes. Where a building or mountain blocks that path, photons cannot arrive. The boundary between those two regions moves across the surface. But the darkness itself is not sliding forward like a wave. Instead, different places simply stop receiving photons. The distinction seems subtle until you scale it up, because once we step beyond Earth, we begin to see how deeply the speed of light shapes reality. For example, imagine watching Earth from far away in space. From a distance of about 300,000 kilometers, the distance light travels in 1 second, you would see Earth as it was 1 second in the past. At 600,000 kilometers, you would see it 2 seconds ago. At the distance of the Moon, the delay grows to about 1¼ seconds. This means that if you could hover above the Moon and look down at Earth, every movement would appear slightly delayed. Lightning flashes, city lights switching on, waves crashing along coastlines, all would be happening a little earlier than you see them. The light must travel the distance before your eyes can receive it. Now imagine drifting farther outward. From the orbit of Mars, sunlight takes around 12 minutes to arrive from Earth. From Jupiter, the delay grows to about 40 minutes. Beyond the outer planets, the delays stretch into hours. Communication with spacecraft in those regions already experiences this effect. Engineers sending commands to distant probes must wait long periods for signals to travel back and forth. Nothing happens instantly across space. Even light needs time. And that simple fact creates an invisible structure in the universe. Every location is surrounded by a sphere of events it can currently observe, events whose light has already arrived. Everything beyond that sphere exists in a sense we cannot yet witness. It is still in darkness relative to us. This idea becomes even more striking when we think about entire galaxies. Our Milky Way galaxy is enormous, about 100,000 light-years across. That means light leaving one side of the galaxy needs 100,000 years to reach the other side. Imagine a star exploding on the far edge of the Milky Way. The explosion would release enormous energy and flood its surroundings with light. Nearby stars would see it almost immediately. But for observers on the opposite side of the galaxy, that event would remain invisible for 100,000 years, until the photons finally arrived. During that time, the explosion would technically already be part of history. Yet for distant observers, it would still lie in the future. In this way, the speed of light quietly divides the universe into layers of time. Different regions witness the same events at different moments depending on their distance. Reality itself is spread out across space by the travel time of light, and that leads to an extraordinary realization. When we look into the night sky, we are not just looking outward, we are looking backward. Each star reveals a slightly earlier version of the universe. Nearby stars show us recent history. Distant galaxies show us ancient epochs. Some galaxies visible in powerful telescopes appear as they were billions of years ago, when the universe itself was young. Their photons have been travelling toward us ever since. For billions of years they crossed the darkness between galaxies. They passed through expanding space, drifting through enormous voids where almost nothing exists. And eventually a few of those photons entered our telescopes. Those rare arrivals allowed astronomers to reconstruct the early stages of cosmic history. Once again, darkness is not an active force shaping the scene. It is simply the backdrop created by distance and time. Where photons have arrived, we see structure. Where they have not, we see blackness. But even that blackness is not completely empty. Intergalactic space, the vast regions between galaxies, contains extremely faint light. Stray photons from distant stars drift through it. Ancient radiation from the early universe passes through it. Yet these photons are so sparse that they rarely interact with anything. To our eyes, the region appears perfectly dark. It is a quiet emptiness filled with travelling light that almost never reaches us. And this brings us to a fascinating consequence. If darkness is simply the absence of arriving light, then darkness does not need to spread through space to exist. It is already everywhere. The universe does not start bright and gradually become dark. It starts dark, and brightness appears only where photons are produced and successfully complete their journeys. Every star is like a lighthouse shining into a vast ocean of night. Every galaxy is a cluster of those lighthouses, and between them stretch enormous regions where no nearby sources send light in our direction. From our viewpoint, those regions appear black, but not because darkness is filling them, because light has not reached us from there. Once we begin to think this way, a strange inversion occurs. Darkness is not the mysterious presence we once imagined. Light is the rare traveller, and every photon that reaches your eyes tonight is the survivor of an incredible voyage through that immense quiet. Think for a moment about what that journey actually means. A single photon leaves the surface of a distant star. It bursts outward with countless others, spreading in every direction at once. Most of them will never encounter anything meaningful. Many will drift through space for millions of years and then disappear quietly into dust, gas, or the cold surfaces of planets that no one will ever see. But a tiny fraction survive an extraordinarily unlikely path. One photon travels across empty space without being absorbed. It avoids wandering clouds of interstellar dust. It passes between planets and asteroids. It continues through the quiet darkness between stars. Years pass, then centuries, then perhaps thousands or millions of years, and eventually, after all that time, the photon reaches a small blue planet orbiting an ordinary star in the outskirts of a galaxy. It enters the atmosphere. It scatters once or twice among air molecules, and finally it lands on a sensor inside a telescope, or on the delicate surface of a human retina. In that instant, the journey ends. But something remarkable happens at the same time, because the moment that photon arrives, the darkness in that direction disappears, at least for us. The region of space that had been invisible suddenly reveals a point of light, and all of that happens not because darkness moved away, but because a single traveller arrived. This is the quiet mechanism behind everything we see in the universe. Light moves. Darkness simply remains wherever light has not yet arrived. Once we begin to understand this, another everyday experience becomes easier to interpret. Picture yourself standing outside just before sunset. The sky is still bright, but the sun is touching the horizon. The long shadows of trees stretch across the ground, and the light feels softer, warmer. Slowly, the landscape dims. Fields fade into grey, buildings lose their sharp edges, colours drain from the world. It feels as if night is spreading across the land. But if we could zoom far above Earth and watch from space, the scene would look completely different. From orbit, you would see a sharp line cutting across the planet. On one side of that line, sunlight floods the continents and oceans. On the other side lies the darkness of night. The boundary moves steadily westward as Earth rotates. Cities slide into shadow. Mountains disappear into darkness. Coastlines fade as the sunlight no longer reaches them. But notice something important. That line is not made of darkness flowing across the surface. It is made of sunlight no longer reaching certain places. The Earth itself blocks the incoming photons from the sun. As the planet turns, different locations rotate out of the sunlight and into the shadow cast by the planet. Night is simply Earth's own shadow. And shadows, as we now understand, are not physical things. They are regions where photons are missing. This means the night side of Earth is not being filled with darkness like water flooding a valley. Instead, it is simply the half of the planet that is no longer receiving sunlight. Where sunlight stops arriving, darkness is already waiting. Seen from space, the Terminator line, the boundary between day and night, moves across Earth at roughly 1,600 kilometers per hour near the equator. That is fast, but it is far slower than light. Sunlight itself is travelling from the sun toward Earth at nearly 300,000 kilometers per second, which means that every second, new shells of sunlight are arriving, spreading across the half of Earth facing the sun. As Earth rotates, some places stop receiving that stream. Darkness appears there instantly. Not because it moved in, because the flow of photons stopped. But there is another subtle layer to this story. Even when the sun sets, the world does not become perfectly dark right away. The sky continues glowing for a while. A soft blue lingers overhead. Then it slowly deepens into darker shades. This twilight exists because Earth's atmosphere scatters sunlight. Even when the sun has dipped below the horizon, sunlight is still striking the upper atmosphere. Some of those photons scatter downward toward the surface. For a time, the sky remains faintly illuminated. Eventually, as Earth rotates further, even that scattered light fades, and only then does the deeper darkness of night fully appear. Again, nothing has travelled toward us. Photons simply stopped arriving from certain directions, and the more we look at the universe through this lens, the clearer the pattern becomes. Light is always on the move. Darkness never needs to move at all. To appreciate just how extreme this contrast is, we can widen our perspective once again, this time beyond the solar system. Our Sun is only one of hundreds of billions of stars in the Milky Way galaxy. From a distance, the galaxy would appear as a swirling disk of light, with spiral arms glowing softly from billions of stars. But those stars are not packed tightly together. They are separated by vast distances. If you stood on a planet orbiting one of those distant stars and looked toward the nearest neighbouring system, you would not see a sky crowded with bright suns. You would see a single distant point of light surrounded by almost complete darkness. Between those stars lies an enormous volume of space where almost nothing exists. A few atoms drift through it. Occasional grains of dust float silently, and every now and then a photon passes through on its long journey from one star to another. But for the most part, interstellar space is quiet. The nearest star to our Sun, Proxima Centauri, is more than 4 light-years away. That means if you could travel at the speed of a light, the fastest speed anything can move, it would still take more than 4 years to reach it. Our fastest spacecraft would require tens of thousands of years. Between those two stars stretches a region where almost no light sources exist. Sunlight travels outward through that region. So does the light from Proxima Centauri. But unless a photon from one of those stars happens to intersect your eye, that region remains dark. Not because darkness lives there, because photons rarely pass through the exact path between the star and you. In other words, most of space is dark simply because it is empty. The sources of light are small and scattered, and once we zoom out even further, the scale of that emptiness becomes almost impossible to grasp. Our galaxy contains hundreds of billions of stars, yet it is only one galaxy among hundreds of billions in the observable universe. Each galaxy is a glowing island of light floating within a vast cosmic ocean. Between galaxies lie enormous voids stretching millions of light-years across. These voids contain very little matter and almost no bright sources of light. Photons from distant galaxies pass through them occasionally, but the density is extremely low. If you were drifting alone inside one of these cosmic voids, the nearest visible galaxy might appear as a faint smear of light millions of light-years away. Every other direction would look almost perfectly black. Not because darkness is spreading through the void, because no nearby sources are sending photons toward you. This is the true architecture of the cosmos. Small pockets of brightness surrounded by immense expanses where light is scarce. And yet, even in these quiet regions, photons are still travelling. Light from ancient galaxies crosses the void slowly. Some of those photons began their journey before Earth even formed. They have been travelling ever since, moving through space at the same unchanging speed. And every once in a while, one of them arrives. When it does, a tiny patch of darkness disappears. A new point of light enters our view, and the universe reveals one more piece of its distant past. Now imagine following one of those photons as it travels, not from the Sun, which is relatively close, but from a star much farther away, perhaps a star on the other side of our galaxy, tens of thousands of light-years from Earth. The photon leaves the surface of that star during a violent eruption of energy inside its core. Nuclear reactions deep within the star release enormous heat, and eventually that energy escapes as light. For a long time, the photon cannot leave the star at all. Inside the star's dense interior, photons bounce endlessly between atoms, scattering again and again. The journey outward can take thousands of years before a photon finally reaches the star's surface. And then, suddenly, the situation changes. Once the photon escapes into space, nothing stops it anymore. It moves in a straight path through the dark between stars, travelling at that same astonishing speed, about 300,000 kilometers every second. At that speed, the photon could circle Earth more than 7 times in a single second. But the galaxy is enormous. Crossing the Milky Way from one side to the other would take light roughly 100,000 years. So our photon begins a long, quiet journey. For thousands of years it passes through interstellar space. There are moments when it drifts through faint clouds of gas. Other times it moves through regions so empty that a single atom might be separated from the next by hundreds of meters. Most of the time, nothing happens at all. The photon just keeps moving. And this is where our intuition about darkness often fails us again. because we tend to imagine space as a place where light stops quickly, swallowed by darkness. But in reality, light almost never stops in space. Unless it hits something, a photon will keep travelling indefinitely. It does not slow down. It does not fade gradually like sound in air. It simply continues until it interacts with matter. So our photon drifts on. During its journey, entire civilizations rise and fall on distant planets. Stars are born, others collapse, gas clouds shift and swirl through the galaxy. Yet the photon remains unchanged. From its own perspective, if such a thing could exist, the entire journey happens instantly. But for the rest of the universe, tens of thousands of years pass. Eventually the photon approaches the region of space containing our solar system. The sun is shining nearby, sending its own flood of photons outward. Planets orbit quietly. Dust and gas drift through the heliosphere. Our photon slips through this region almost unnoticed. Then it reaches Earth. It passes through the upper atmosphere, where some photons scatter and turn the sky blue, but our traveller avoids those collisions. It continues downward, threading through the air until finally it strikes a tiny detector inside a telescope. In that moment, the detector records the arrival. Astronomers studying that signal may learn something about the distant star that produced it, its temperature, its chemical composition, its motion through the galaxy. A journey that lasted tens of thousands of years ends in a fraction of a second. And once again, what had been darkness suddenly becomes information. A tiny spark of light appears where before there was none. Or because one photon arrived. When we multiply this story by trillions upon trillions of photons, we begin to see how the universe gradually reveals itself. Every visible object in the sky is known to us only because its photons have managed to reach our telescopes. If the photons are blocked, absorbed, or simply travelling somewhere else, the object remains hidden. Which means the darkness we see across the sky is not necessarily empty. It is often just unseen. There may be stars there whose light is travelling in other directions. There may be galaxies whose photons have not yet had time to reach us. There may be entire regions where light exists but never intersects our eyes. Darkness, once again, is simply a place where light has not arrived. This idea leads to another question that seems obvious once we ask it. If light is always travelling outward from stars and galaxies, why isn't the night sky completely bright? Why do we see darkness between the stars at all? At first glance, the universe contains so many stars that the sky might be expected to glow everywhere. Every line of sight should eventually intersect the surface of a star, just as every direction in a dense forest eventually meets a tree. Yet when we look up, most of the sky is black. This puzzle fascinated astronomers for centuries. It became known as Olbers's paradox. The answer reveals something profound about the structure of the universe. First, the universe has a finite age. Stars have not been shining forever. There has only been about 13.8 billion years since the earliest light could begin travelling freely through space. That means light from extremely distant stars has not yet had enough time to reach us. Their photons are still crossing the enormous distances between galaxies. Until they arrive, those regions remain dark. Second, the universe is expanding. Galaxies are gradually moving away from one another as space itself stretches. As light travels through this expanding space, its wavelength stretches as well. Over billions of years, visible light can shift into infrared or even radio waves, forms of radiation our eyes cannot see. The light is still there, but it has become too faint or too stretched for human vision. And finally, stars themselves are limited. They are born. They shine for millions or billions of years, and eventually they change or fade. The universe has not had enough time for starlight to accumulate everywhere. All of these factors combine to produce the night sky we see, a scattered pattern of lights against a vast background of darkness. But remember what that darkness actually represents. Not a substance, not a flowing shadow, simply regions where photons have not reached us, or where the arriving light is too faint for our eyes to detect. In this way, the night sky is a map of light's journeys. Each star marks a successful path through space and time. Each dark region marks a path where photons have not yet arrived. And once you begin to see the sky like this, another realization slowly emerges. We are living inside a constantly expanding bubble of visibility. Every year, light from more distant regions of the universe arrives for the first time. New photons reach Earth that have been travelling for billions of years. Each arrival slightly enlarges the portion of the universe we can observe. Darkness retreats, not because it moved, but because light finally arrived. It is a quiet expansion of knowledge. The visible universe grows photon by photon. And yet, beyond that growing horizon lies an even greater expanse. A vast region of reality whose light is still travelling toward us across unimaginable distances. From our perspective, those regions remain dark. Not because they lack light, but because the photons carrying their stories are still on the way. And this is where the story begins to feel almost poetic, even though it is built entirely from physics. Because the universe we can see is not fixed, it is slowly growing. Every second, photons that have been travelling across space for billions of years finally arrive at Earth. Each arrival reveals something that, until that moment, had never been seen by any human being. For all of human history, those photons were still on their way. Civilizations rose, languages formed, cities appeared and disappeared. Meanwhile, light from distant galaxies continued crossing the darkness between them and us. Only now, only in this narrow moment of cosmic time are some of those journeys ending. A telescope turns toward a faint patch of sky. A detector waits patiently, and suddenly ancient photons arrive. What was once darkness becomes structure. A faint galaxy appears. A cluster of stars resolves. A region that seemed empty becomes filled with delicate patterns of light. Nothing changed out there in that distant place. What changed was here. The photons finally reached us. This quiet process happens constantly. Modern telescopes are always extending our reach into the darkness, collecting light that began travelling before Earth even formed. The James Webb Space Telescope, for example, is able to detect extremely faint infrared light from galaxies that formed when the universe was very young. Those galaxies were already shining billions of years ago. Their photons simply needed time to arrive. The telescope is not creating new light. It is catching travellers that have been moving toward us since the early universe. And every time we detect one of those photons, the visible universe becomes a little larger. Darkness recedes. Not because it moved away, because light arrived. But this expansion of visibility has limits. There is a boundary beyond which light will never reach us, no matter how long we wait. To understand why, we need to think about how space itself behaves. The universe is not static, it is expanding. Galaxies are gradually moving farther apart as the fabric of space stretches between them. This expansion was first discovered nearly a century ago, when astronomers noticed that distant galaxies were all drifting away from us. The farther away a galaxy is, the faster it appears to recede. At small distances, this expansion is subtle. Nearby galaxies move away from us slowly. But at enormous distances, the effect becomes dramatic. Some galaxies are receding so quickly that the light they emit today will never reach us at all. Not because light slowed down. Light still travels at the same cosmic speed limit. But because the space between us and those galaxies is stretching faster than the photons can close the gap. It is like trying to swim across a river whose current grows stronger the farther you go. At some point, the water carries you away faster than you can move forward. Beyond a certain distance, galaxies are effectively moving away faster than their light can approach us. Photons they emit now will never arrive. They are carried away by the expansion of space itself, which means there are regions of the universe permanently hidden from our view. Their stars shine. Their galaxies evolve, but their light will never reach Earth. From our perspective, they remain forever dark. This boundary is sometimes called the cosmic event horizon. Not the edge of the universe, but the edge of what can ever become visible to us. Inside that horizon, light can eventually reach Earth. Outside it, the expansion of space prevents those photons from ever arriving. So even if the universe continues forever, there will always be regions we cannot see. Darkness will remain, not because light does not exist there, but because the photons cannot cross the expanding gulf between us. It is one of the quiet consequences of living in an expanding cosmos. Our window onto reality is limited by the travel time of light and the growth of space. Yet even within the visible universe, light behaves in ways that continue to surprise us. Sometimes photons travel through space in such a way that the darkness around them bends and distorts the view. This happens because light does not always move in perfectly straight lines when gravity is involved. According to Einstein's theory of general relativity, massive objects like stars and galaxies curve the fabric of space itself. When light passes through those curved regions, its path bends. This effect is called gravitational lensing. Imagine placing a glass lens over a sheet of paper. The lens bends the light passing through it, distorting the image beneath. Gravity does something similar. When light from a distant galaxy passes near a massive cluster of galaxies, the gravitational field bends the photon's path. From Earth, we may see multiple images of the same galaxy, or stretched arcs of light surrounding the cluster. In these regions, the boundary between light and darkness becomes warped. Some places appear brighter because light has been focused toward us. Other regions remain dark because photons are being bent away. Once again, darkness is not actively moving or spreading. It is simply the pattern left behind by where photons travel. And that pattern can become incredibly complex on cosmic scales. In deep images of the universe taken by powerful telescopes, astronomers often see faint arcs and rings of light around massive galaxy clusters. Each arc is actually the distorted image of a distant galaxy far behind the cluster. The light from that galaxy travelled billions of years toward Earth, but along the way its path curved around the cluster's gravity. Instead of arriving from one direction, the photons reached us along multiple paths. We see several versions of the same galaxy at once. In the spaces between those arcs lies darkness. Not because darkness gathered there, but because no photons from those distant galaxies travelled along those particular paths. Once again, light defines what we see. Darkness fills the rest. And the deeper we look into the cosmos, the more we begin to realize that visibility itself is shaped by the journeys of photons. The entire structure of our observable universe is determined by which photons have had time and opportunity to reach us. Some travelled straight across empty space. Some curved around galaxies. Some were absorbed by clouds of dust long before they could arrive. Others are still travelling now, crossing distances so vast that their journeys will not end for billions of years. And yet, for all this motion, the darkness itself remains completely still. It does not chase the light. It does not spread when stars die. It does not move across the universe. It simply marks the regions where photons have not yet arrived, which means that every bright object in the sky is not just a place. It is the endpoint of an extraordinary journey, a tiny messenger from a distant time and place, finally arriving after crossing an ocean of darkness that never moved at all. Once you begin to see the universe this way, something quietly profound happens to the meaning of the night sky. It stops looking like a flat backdrop of black with scattered lights. Instead, it begins to resemble a vast network of journeys. Every star is the visible endpoint of millions or billions of photon paths. Every faint galaxy is the arrival point of travellers that crossed unimaginable distances without interruption. And between those visible destinations lies an enormous territory where the journeys simply haven't intersected with us. That territory is what we call darkness. But it helps to remember that this darkness is not empty in the way our intuition first suggests. Photons are still moving through it constantly. They just happen to be moving along paths that do not lead to our eyes. Imagine standing in a massive open desert during a gentle sandstorm. Grains of sand are flying through the air everywhere, carried by shifting winds. Yet only a few of those grains will strike your skin. If you judge the storm only by what you felt on your hands, you might think the air was nearly calm. The desert is full of motion. You simply intersect with only a tiny fraction of it. Space works in a similar way. Photons are constantly crossing enormous volumes of space, travelling outward from stars, galaxies, and ancient events. But the probability that any one of those photons happens to land exactly on your retina at the precise moment you're looking in that direction is extraordinarily small. So the sky looks dark, not because light is absent, but because most of it misses us entirely. This idea becomes easier to grasp if we imagine what the universe might look like to a being that could see every photon moving through space. Such a view would not resemble the night sky we are familiar with. Instead of scattered stars against blackness, the cosmos might appear like a delicate storm of moving sparks, streams of light travelling outward from countless sources in every direction. Some streams would be dense near bright stars. Others would thin into almost invisible trickles across the enormous gaps between galaxies. But the darkness we see would mostly vanish, because the darkness is simply the result of our limited vantage point. Our eyes only detect photons that arrive directly. Everything else passes silently by. And once we recognize that, another curious feature of shadows begins to make more sense. Earlier, we noticed that a shadow is not a physical object. It is just the region where light is blocked. But if we watch shadows carefully, they sometimes behave in ways that feel almost impossible. Imagine a tall flagpole standing under the sun. As the sun moves across the sky, the shadow of the pole stretches across the ground. Close to the pole, the shadow moves slowly, but imagine the same shadow extending across a distant hillside kilometers away. The far edge of that shadow might sweep across the hillside at incredible speed. Under the right conditions, the shadow's edge could move faster than light. At first, this sounds like a contradiction. After all, we have learned that nothing can move faster than light. Yet shadows can appear to do exactly that. The reason is the same subtle principle we encountered earlier. The shadow itself is not an object moving through space. It carries no matter, no energy, and no information by itself. It is simply the shifting boundary between regions where photons arrive and where they do not. When the sun's angle changes slightly, different parts of the ground either receive photons or stop receiving them. That change can sweep across enormous distances very quickly. But nothing physical is traveling across that ground. Different photons are arriving at different places. Darkness itself is not moving. This distinction may seem abstract at first, but it becomes very important when we consider the deepest laws of physics. The speed of light is not just the speed of a particular kind of particle. It is the maximum speed at which information can travel through the universe. No signal, no physical object, no cause and effect relationship can propagate faster than light. But shadows do not transmit information by themselves. They are only patterns created by how light interacts with objects. So when a shadow sweeps across a distant surface faster than light, no physical law is violated. Nothing real is outrunning photons. The shadow is simply a geometric consequence of light being blocked along different paths. And once we understand this, the original question becomes clearer than ever. If light has a speed, what about darkness? Darkness has no speed because it is not something that travels. It appears wherever light is missing. But as we keep widening our perspective, another fascinating implication emerges. Because if darkness is simply the absence of arriving light, then the amount of darkness we see depends entirely on where photons have managed to go, which means that darkness is deeply connected to the shape and structure of the universe itself. For instance, think about what happens when a star is born. Deep inside a cold cloud of gas and dust, gravity slowly pulls material together. The cloud collapses inward, heating up as it shrinks. Eventually the pressure and temperature become high enough for nuclear reactions to ignite. A star is born. The moment those reactions begin, the star starts producing enormous quantities of light. Photons stream outward from its surface in all directions. Where previously that region of space had been dark, it now begins sending light across the galaxy. Nearby planets and gas clouds are illuminated for the first time. Dust grains reflect the starlight, creating glowing nebulae. And slowly, year by year, the expanding sphere of photons travels outward. After 1 year, the light has reached a distance of 1 light year. After 10 years, 10 light years. After 1,000 years, 1,000 light years. The star's light continues spreading across the galaxy like ripples across an ocean. Everywhere those photons arrive, darkness gives way to illumination. But again, nothing has pushed the darkness aside. The photons simply reach new places. And this means that even a single star quietly reshapes the visibility of the galaxy around it. Over time, its light touches more and more distant regions of space. But because the galaxy is so large, most of its light will never reach most of the galaxy at all. Instead, it will disperse into the immense emptiness between stars. And there, for millions of years, those photons will continue traveling through darkness that never moved. Eventually some may encounter a drifting dust grain. Others may strike the surface of a wandering planet. A few might even reach another civilization's telescope somewhere far across the galaxy. Wherever they arrive, darkness briefly disappears. A point of light appears, and the universe becomes slightly more visible. Multiply this process by the hundreds of billions of stars in the Milky Way, and by the hundreds of billions of galaxies scattered across the cosmos, and you begin to see the universe as an immense web of traveling light. Every second, Trillions upon trillions of photons leave their sources and begin journeys through the dark. Most of them will wander forever without being noticed. But every now and then, one of them arrives somewhere meaningful. It lands on a surface. It enters an eye. It strikes a detector. And in that instant, the quiet darkness between worlds reveals something new. A distant star. A hidden galaxy. A glimpse of the universe as it once was. And every such moment reminds us of something surprisingly simple. Darkness never needed to move at all. It was already there, patiently waiting until light finally found its way through. But there is another layer to this story that only becomes clear when we think about time itself. Because the speed of light does more than determine how fast photons travel. It also quietly determines how events unfold across the universe. Nothing we see is happening exactly when we see it. Every image is delayed. The moon we see in the sky is about 1¼ seconds in the past. Sunlight reaching your face left the sun a little more than 8 minutes ago. The light from Jupiter shows us the planet as it was roughly 40 minutes earlier. Even on these relatively small cosmic scales, reality already comes with built-in delay. If something dramatic were happening on the surface of the sun right now, we would not know about it for 8 minutes. The photons carrying that information are still crossing the distance. And the farther away something is, the deeper into the past we're seeing. A star 1,000 light-years away appears exactly as it was 1,000 years ago. If that star changed yesterday, we would not notice for another millennium. This simple fact means that the universe we observe is not a single synchronized moment. It is a layered history. Different distances reveal different times. Nearby objects show us the recent past. Distant galaxies reveal the ancient universe. And everywhere beyond the reach of light's journey remains invisible to us. Which again brings us back to the quiet role of darkness. Darkness is not hiding things from us in an active sense. It is simply the natural consequence of a light needing time to travel. In every direction you look, there are regions whose photons are still on the way. Those places exist right now, but their light has not yet crossed the distance between there and here. Until it does, those regions remain dark to us. Now imagine this idea stretched across the full scale of the cosmos. The observable universe extends roughly 46 billion light-years in every direction. That number can feel strange at first, because the universe itself is about 13.8 billion years old. But the expansion of space has stretched distances while light has been travelling. The result is an immense sphere of visibility centred around us. Everything inside that sphere has had enough time to send light our way. Everything beyond it has not. Picture a vast cosmic fog slowly revealing shapes as light reaches you. Except the fog is not moving. The illumination is expanding. With each passing moment, the front edge of arriving light from extremely distant regions gets slightly closer. And somewhere in that slow advance, photons that began travelling billions of years ago are still crossing the darkness toward us. Some are arriving tonight. But the idea becomes even more interesting when we remember that the expansion of the universe is accelerating. Galaxies are drifting away from one another faster and faster as space stretches. This means that over extremely long periods of time, many distant galaxies will fade from view entirely. Their light will become stretched into longer and longer wavelengths. Eventually the photons will become so faint that even our most powerful telescopes will no longer detect them. The galaxies themselves will not disappear. They will continue existing out there, but their photons will no longer reach us in a way we can observe. In the far future, observers in our galaxy may see a much darker universe. Many of the galaxies we can see today will have slipped beyond the horizon of visibility. Their light will have stretched into invisibility, or will simply never reach us again. From their perspective, darkness will seem to grow. But once again, darkness will not have moved. What will have changed is the arrival of light. Photons that once reached us will no longer do so. The visible portion of the universe will shrink. And this strange outcome comes from the same simple rule we began with. Light travels at a finite speed. Darkness does not travel at all. Now let's return briefly to a much smaller scale. Imagine again the moment when you turn off a lamp in a dark room. It feels instantaneous. The room simply becomes dark. But even here, something subtle is happening. For a fraction of a billionth of a second after the switch flips, photons already in motion continue crossing the room. They bounce from walls and objects, scattering in different directions. Your eyes receive the last few arrivals. Then the stream ends. The room appears dark. If we had instruments fast enough to measure this change precisely, we would see the final photons fading in a tiny ripple moving through the space. The change would propagate outward at the speed of light. In a room this small, the effect is too fast for human senses to notice. But in larger spaces, the delay becomes more visible. Astronomers sometimes observe this phenomenon on cosmic scales in what are called light echoes. Imagine a massive star exploding in a supernova. The explosion releases an enormous burst of light. Nearby clouds of gas and dust reflect some of that light, scattering it in different directions. Some of those reflected photons take longer paths before reaching Earth. So astronomers may see expanding rings of light appearing years after the original explosion. The light from the event is still arriving, just along longer routes. Once again, darkness in those regions disappears only when photons finally reach them. These echoes create beautiful expanding shells of illumination across nearby clouds. They look almost like ripples spreading through space. But they are not waves of darkness moving outward. They are delayed arrivals of light. The same principle appears in other places as well. Sometimes a star in the center of a galaxy suddenly becomes brighter as gas falls toward a massive black hole. The surrounding clouds respond slowly as the new light spreads outward. Astronomers watch regions of gas brighten one after another as the photons reach them. It is like watching dawn spread across a cosmic landscape. But dawn is not something that moves through space. It is simply the arrival of sunlight. And when the light stops, darkness remains behind, not because it advanced, but because illumination ended. Across every scale, from a room to a planet to an entire galaxy, the pattern remains the same. Light travels. Darkness waits. And this difference between movement and absence shapes almost everything we see in the universe. Because in the end, the visible cosmos is nothing more than the sum of all the photons that have successfully completed their journeys. Every bright star, every glowing nebula, every distant galaxy. Each one is the result of light travelling through unimaginable distances of stillness. And every region that appears black is simply where those journeys have not yet intersected with us. Which means that when you look up at the night sky, you are not just looking at lights in the distance. You're watching the quiet boundary between where light has arrived and where it is still on its way. That boundary between arrival and absence is one of the quiet structures shaping the entire universe. We rarely notice it in everyday life because our surroundings are filled with nearby sources of light, lamps, screens, streetlights, the sun itself. Photons are constantly arriving from many directions at once. Darkness seems like something that appears only when those sources disappear. But once we step outside on a clear night and let our eyes adjust, we begin to see the deeper pattern. The sky is mostly dark. A few stars shine. Perhaps the pale band of the Milky Way stretches across the sky. A planet glows steadily near the horizon. Everything else is black. Yet that blackness is not an empty curtain draped across space. It is a map of where light has not reached us, or where the light is too faint for our eyes to detect. And that faintness is important, because light spreads out as it travels. When a star emits photons, those photons move outward in every direction. Imagine a sphere expanding away from the star at the speed of light. The surface of that sphere grows larger every second. The same number of photons must cover a bigger and bigger area as time passes. This means the light becomes thinner. Close to the star, the photons are dense and bright. Far away, they are spread out across enormous distances. By the time starlight reaches Earth from distant stars, the photons are incredibly sparse. A single star that shines brilliantly in its own solar system may deliver only a handful of photons each second to a telescope on Earth. That is enough for us to see it, but not enough to illuminate the sky around it. Between those scattered photons lies darkness, not because darkness flowed there, but because light thinned as it travelled. This spreading of light also explains why galaxies appear so faint when they are very far away. A galaxy may contain hundreds of billions of stars. Up close, it would fill the sky with blinding brilliance. But when that galaxy lies millions or billions of light years away, the photons from all those stars are spread across an enormous sphere of space. Only a few of them reach Earth. To our eyes, the galaxy becomes a dim smudge of light barely visible through a telescope. Beyond a certain distance, even our best instruments struggle to detect it. The galaxy has not stopped shining. Its photons simply arrive too sparsely to notice. In those directions, darkness remains dominant. Another factor deepens this effect. As the universe expands, the wavelengths of travelling photons stretch. Light that began its journey as visible radiation can gradually shift into infrared or radio waves. These wavelengths carry less energy and fall outside the range of human vision. The photons still exist. They are still moving through space, but our eyes cannot see them. From our perspective, those regions appear dark. Yet with the right instruments, infrared telescopes or radio antennas, astronomers can detect some of that hidden radiation. Suddenly areas that seemed black reveal structure. Cold gas clouds appear. Distant galaxies glow faintly. Ancient radiation from the early universe becomes visible. Again, nothing about the darkness itself has changed. Only our ability to detect the arriving photons. This is one of the reasons astronomy constantly evolves. Every new telescope extends our reach into regions that once appeared completely dark. Radio telescopes reveal objects invisible to optical instruments. Infrared detectors uncover stars hidden behind clouds of dust. X-ray observatories detect violent events near black holes and neutron stars. Each new technology collects photons that were always there but previously went unnoticed. With each improvement, darkness gives way to new patterns of light. But even the most powerful instruments cannot eliminate darkness entirely, because there are still limits set by physics. One of those limits comes from the earliest period of cosmic history. Not long after the universe began, matter and radiation were mixed together in a hot, dense plasma. Photons could not travel freely because they scattered constantly from charged particles. It was like trying to see through a thick fog. Only after the universe cooled enough for atoms to form did photons finally escape and begin traveling freely through space. The light released during that moment has been crossing the cosmos ever since. Today we detect it as the cosmic microwave background, a faint glow present in every direction. But that radiation marks a boundary in time. Before that moment, light could not travel far enough to carry clear information across the universe, which means that everything earlier than that time remains hidden behind a kind of luminous fog. Even if we built perfect telescopes, we could not see directly beyond that barrier using light alone. Darkness, once again, is not an invading force. It is the natural result of physical limits on how photons move through the universe. And once we understand that, the original question becomes almost serene in its simplicity. Light has a speed. It moves through space at a constant universal limit. Darkness has no speed because it never needed to move. It is simply the background condition that exists until photons arrive. When light appears, darkness vanishes. When light stops, darkness remains. Nothing travels in either direction. The change is simply the presence or absence of photons reaching our eyes. And this quiet truth reshapes how we think about the night sky. Each point of light becomes the final step in a long journey. Each dark region becomes a place where that journey has not yet ended. The universe reveals itself not by pushing darkness away, but by sending travelers across unimaginable distances. Photons leave stars, galaxies, and ancient cosmic events. They cross the stillness between worlds. And if they are fortunate, if nothing blocks them, absorbs them, or bends them away, they arrive. In that instant, a tiny patch of darkness disappears. A new point of light enters the map of what we can see. And slowly, photon by photon, the universe becomes visible to us. Yet even as we watch that process unfold, the greater portion of reality remains hidden beyond the reach of light that has not yet arrived. A vast territory of existence waiting quietly in the dark. Not because darkness travelled there, but because the photons carrying its story are still on the way. If you pause for a moment and imagine the universe without this limit, without the speed of light, the entire structure of reality would look very different. Events would have no delay. Light from every star could reach every place instantly. Information would spread across the cosmos without resistance. In such a universe, the night sky might not exist at all. Every direction you looked would eventually intersect the surface of a star or a glowing cloud of gas. Light from distant galaxies would arrive immediately, filling the sky with brightness from every corner of the universe. Darkness would almost disappear. But our universe is not built that way. Instead, It runs on a rule that quietly shapes everything we observe. Nothing carries information faster than light. Because of that rule, light needs time to cross distance, and distance in the universe is enormous. The result is a cosmos where visibility unfolds slowly. Stars illuminate their surroundings, but their light spreads outward at a finite pace. Galaxies glow across space, but their photons require millions or billions of years to reach distant observers. And between those arriving photons lies darkness. Not because darkness is expanding, because light is still travelling. Once you begin to think about it this way, the night sky stops looking like a finished picture and begins to resemble an unfinished one. We are watching it being painted, photon by photon. Every moment, new light from distant regions is crossing space toward us. Some of it has been travelling since long before the Earth formed. Some began its journey when the first stars ignited in the young universe. That light is still on its way, and eventually some of it will arrive. When it does, places that once appeared completely dark will reveal faint galaxies or clusters of stars that had always been there. This is one of the reasons astronomers often return to the same patch of sky again and again with more sensitive instruments. What once looked empty can slowly reveal deeper layers of structure. In the famous deep-field images taken by space telescopes, astronomers pointed their instruments at regions that seemed almost completely dark. At first, only a few faint points of light appeared. But with longer exposures, collecting photons for hours, days, even weeks, the darkness began to fill with galaxies. Thousands of them. Some near, some so distant that their light began travelling toward Earth billions of years ago. Those galaxies were always there. Their photons simply needed enough time to accumulate in the telescope. The darkness slowly gave way, not because it moved aside, but because more light arrived. In a sense, every telescope is a photon collector. The longer it waits, the more travellers it receives. And with each arrival, the visible universe grows richer. But there is another remarkable feature of light that deepens this picture even further. Photons do not age. A photon emitted from a distant galaxy billions of years ago does not become tired or worn during its journey. It does not gradually slow down. It continues moving at the same speed for the entire duration of its path. Only when it finally interacts with matter, perhaps striking a telescope mirror or entering a human eye, does its journey end. Which means that some of the photons we detect today have been travelling through darkness for nearly the entire history of the universe. From their perspective, the trip contains no passage of time. Yet from ours, it represents billions of years of cosmic history. This strange relationship between light, distance, and time is why astronomers can study the early universe at all. The farther we look into space, the farther back in time we see. A galaxy 10 billion light-years away appears as it was 10 billion years ago. We are observing it when the universe itself was much younger. In this way, light acts as a messenger carrying ancient information across vast distances. Each photon that arrives tells us something about where it came from. Its color reveals temperature. Its direction reveals location. Its subtle shifts reveal motion. And the fact that it arrived at all tells us something important. That the path between that distant place and us remained open long enough for the photon to complete its journey. Darkness marks the places where that journey never intersected with us. And once you begin to see the universe as a network of these journeys, the sky above you becomes something more than a collection of distant lights. It becomes a living record of motion. Photons leaving stars. Photons crossing galaxies. Photons slipping through vast cosmic voids. Some paths succeed, others end silently along the way, but each successful arrival reveals another piece of reality, which brings us back, gently, to the simple question that began this exploration. If light has a speed, what about darkness? The answer now feels almost obvious. Darkness has no speed because it does not travel. It never needed to. Darkness is simply the state that exists wherever photons are not arriving. When light appears, darkness vanishes. When light stops, darkness returns. Nothing moves between those states except the photons themselves. And that realization quietly reframes the entire cosmos. The universe is not a battlefield where light fights against darkness. It is a vast, mostly quiet space where light journeys outward from its sources. Where those journeys reach us, we see. Where they do not, we see black. In other words, The night sky is not filled with darkness that moved toward us. It is filled with distance. Distance across which light is still travelling. Distance across which ancient photons are still crossing the silent spaces between galaxies. And somewhere, far beyond the faintest stars we can see tonight, there are photons already on their way toward Earth. They began their journey long before humanity existed. They crossed the darkness between galaxies. They slipped through cosmic voids where almost nothing moves. And one day, perhaps thousands of millions or billions of years from now, some of them will finally arrive. When they do, a tiny piece of the darkness above us will quietly disappear. A new point of light will appear in the sky, and the visible universe will become just a little bit larger than it was before. And if you stay with that idea for a moment, something subtle begins to change about how the night sky feels. At first glance, the darkness above us seems like emptiness, a quiet background that simply sits behind the stars. But once we understand what is really happening, the darkness begins to feel less like emptiness and more like distance made visible. Every dark patch of sky is a direction where the journeys of light have not yet intersected with us. Not because there is nothing there, but because the photons from those places have not arrived. Some are still travelling. Some may never reach us at all. And yet, in that stillness, light continues moving. Right now, at this exact moment, photons are leaving stars across the galaxy. They are pouring away from the surfaces of suns in every direction, forming expanding spheres of light that grow larger every second. Most of those photons will never encounter anything meaningful. They will drift through the darkness between stars for thousands or millions of years. They will pass through regions where matter is so sparse that entire kilometers of space contain only a few stray atoms. And still they keep going. It is difficult for the human mind to truly picture this kind of emptiness. On Earth, even the quietest places are full of motion, air currents, drifting dust, the subtle hum of energy moving through the environment. But interstellar space is different. Between stars, the average density of matter can be less than a single atom per cubic centimetre. In some places, it is far lower. If you could stand there, suspended in the dark between two distant stars, you would find yourself surrounded by an almost unimaginable silence. No wind, no sound, no nearby sources of light, only a faint sprinkling of distant stars across the sky. And through that silence, photons would still be passing. Some would come from nearby stars, others from distant parts of the galaxy. A few would arrive from galaxies millions of light years away. You would not see most of them. They would simply slip through space, crossing paths with you for an instant before continuing on. Light would be moving everywhere, yet the universe would still appear dark, because your eyes would intersect only a tiny fraction of those travelling photons. This quiet mismatch between how much light exists and how little of it we perceive explains why the cosmos looks the way it does. The universe is not mostly dark because light is rare. It is mostly dark because space is enormous. Stars are small compared to the vast distances between them. Galaxies are bright islands scattered across unimaginable expanses, and light spreads outward in all directions, becoming thinner as it travels. By the time it reaches us from distant places, only a few photons remain along any given path. That is enough to reveal a star, but not enough to erase the darkness surrounding it. In this way, darkness becomes a kind of canvas. Light draws delicate patterns upon it, and those patterns slowly change as photons arrive from new places. Sometimes those arrivals are dramatic. When a massive star reaches the end of its life, it may explode in a supernova. For a brief time, that single star can outshine an entire galaxy. The explosion releases an immense burst of light that spreads outward through space. Nearby gas clouds glow as the radiation reaches them. Dust reflects the expanding wave of illumination. Across the galaxy, photons from that explosion begin new journeys. Some will reach distant stars. Some will drift into the quiet void between galaxies. And a few, perhaps only a few, will eventually reach a telescope on a small planet orbiting a modest star. When they arrive, astronomers will suddenly see a new point of light in the sky where darkness once seemed complete. The event may have happened thousands of years earlier, but the light has only just arrived, and in that instant, the darkness in that direction quietly disappears. Not because darkness moved away, because the photons finally reached us. The same process occurs on even larger scales. Entire galaxies sometimes collide and merge over hundreds of millions of years. During these encounters, clouds of gas compress and ignite waves of a new star formation. Thousands of bright young stars may appear within swirling arms of dust and gas. Each of those stars begins sending photons outward. The galaxy brightens. New light spreads across intergalactic space. But again, those photons must travel. The glow of that distant galaxy may take millions or billions of years to reach observers far away. Until it does, those observers will see only darkness in that direction. And this reveals something beautiful about the structure of the universe. Visibility itself spreads through space like a growing frontier. Not because darkness retreats, but because light advances. Every star pushes that frontier outward as its photons expand into surrounding space. Every galaxy adds to the slow illumination of the cosmos. And every observer, every planet, every telescope, every eye, sees only the tiny portion of that illumination that has had time to arrive. This idea becomes especially striking when we think about how young humanity is compared to the age of the universe. Our species has existed for only a few 100,000 years. Civilization, as we usually define it, is only a few thousand years old. That is an incredibly small slice of cosmic time. During those brief millennia, photons from distant galaxies have continued their journeys toward Earth. Some that began travelling long before humans evolved are only now arriving. Others that left their sources when the first cities appeared on Earth are still crossing the darkness between galaxies. They have not reached us yet. They are still on their way, which means that the sky above us is not finished revealing itself. The visible universe is still unfolding. New photons will continue arriving tomorrow. And next year, and long after our own civilization has changed in ways we cannot imagine, each arrival will erase a tiny piece of darkness and replace it with information about some distant place. Perhaps a faint galaxy, perhaps a star cluster, perhaps the ghostly afterglow of an ancient cosmic event. In this sense, the darkness above us is not static. It is simply waiting for light that has not yet arrived. And somewhere, far beyond the faintest stars visible tonight, photons are already travelling toward us across distances so vast that the journey will take millions or billions of years. They are crossing silent voids between galaxies. They are slipping past drifting clouds of intergalactic gas. They are moving steadily, second after second, at the same unchanging speed. One day, some of them will reach Earth. And when they do, another small fragment of the universe will become visible for the first time. A quiet reminder that what we call darkness was never a thing moving through space. It was simply the space between arrivals. And that idea, that darkness is simply the space between arrivals, quietly reshapes how we think about the present moment. Because every moment we live in is filled with light that has just completed an extraordinary journey. Right now, photons are entering your eyes that left their sources long ago. Some began their journey 8 minutes earlier at the surface of the sun. Others may have left distant stars years before you were born. You're not just seeing the world. You are receiving travellers. Each photon arriving at your retina carries a tiny piece of history. The angle it arrives from tells your brain where it came from. Its colour carries clues about temperature and energy. Its timing reveals motion. Your brain quietly assembles all of these arrivals into a picture. A tree. A room. A face. A star. But beneath that picture lies an invisible story of motion. Photons left those objects and crossed the space between them and you. And where photons did not arrive, your brain filled in darkness. Even the most ordinary experiences follow this pattern. When you walk into a dark room and flip a light switch, what you're really doing is beginning a new outward flow of photons. The bulb heats up. Light bursts outward in all directions. Photons strike the walls, the floor, the furniture. They bounce and scatter. Within billionths of a second they reach your eyes. Your brain suddenly receives information it did not have before. The room appears. Nothing about the darkness moved away. Light simply arrived. And this small example mirrors the behaviour of the universe on the largest scales imaginable. Stars ignite. Galaxies glow. Black holes swallow light in their deep gravitational wells. Across it all, photons travel through the immense quiet between objects. Sometimes they reach observers. Sometimes they do not. Where they arrive, reality becomes visible. Where they do not, darkness remains. Once we begin to think in these terms, we realize that the universe is less like a place filled with objects and more like a network of paths taken by light. The structures we see, stars, nebulae, galaxies, are not just things, they are sources. They are places where photons begin their journeys. And every observer is a destination, a place where those journeys can end. Between the sources and the destinations lies an immense web of possible paths. Some paths succeed. Most never intersect with anything meaningful. The cosmos is constantly sending light outward in all directions, like billions of lighthouses shining across an ocean that has no shore. And the darkness we see between them is simply the ocean itself. Vast, still, waiting, occasionally illuminated when a traveller passes through. This way of seeing the universe also reveals something subtle about knowledge itself. Everything we know about the cosmos comes from light. Astronomers cannot visit distant stars or galaxies. They cannot touch them or sample them directly. Instead, they study the photons those objects send our way. The colour of the light reveals temperature. Tiny shifts in wavelength reveal motion. Patterns of brightness reveal structure. Even the presence of unseen planets around distant stars can be inferred by watching how starlight changes over time. All of this knowledge arrives carried by photons that have crossed immense distances. Each photon is a messenger, and the darkness between those messengers is simply the silence between signals. If no photons arrive from a direction, we know nothing about it. If photons do arrive, they carry clues. Piece by piece, scientists reconstruct the structure of the universe by studying those clues. A faint line in a spectrum might reveal the presence of hydrogen in a distant galaxy. A slight wobble in a star's brightness might reveal an unseen planet orbiting around it. A subtle distortion in the paths of photons might reveal the presence of invisible matter-bending space. All of these discoveries begin the same way. A photon arrives. Darkness gives way to information. And over time, millions of such arrivals accumulate into understanding. The night sky, once thought to be an empty dome scattered with lights, becomes something far richer. A constantly evolving record of journeys completed, of photons crossing billions of years of space, of light leaving distant galaxies when the universe itself was young and finally reaching us now. And perhaps the most remarkable part of this story is how fragile those journeys are. A single grain of cosmic dust could absorb a photon and end its travel forever. A dense cloud of gas could scatter it in a different direction. Gravity could bend its path away from Earth. Yet some photons still succeed. They slip through the vast complexity of the universe and arrive here, into telescopes, into detectors, into human eyes. And in doing so, they erase a tiny patch of darkness. One more point of light appears. One more piece of the universe becomes visible. It is easy to overlook how extraordinary this process is. After all, light surrounds us every day. Our lives are filled with it. But when we step outside under a clear night sky and allow our eyes to adjust, the deeper truth quietly reveals itself. The darkness above us is not empty. It is simply the vast space between countless journeys of light. Some of those journeys have already ended. They form the stars and galaxies we see tonight. Others are still underway. Photons are crossing unimaginable distances even now. And far beyond the faintest stars visible to our eyes, new travellers are beginning their journeys. They leave the surfaces of distant suns. They escape the glowing clouds of newborn stars. They drift outward into the quiet ocean between galaxies. For millions or billions of years, they will travel through darkness that never moves. And one day, perhaps long after our own time, some of them will arrive somewhere. A telescope will detect them. An observer will see a faint new glow in the sky. And in that moment, darkness will vanish from that direction. Not because it fled, but because light finally found its way through. And the more we sit with that idea, the more the night sky begins to feel like a living archive of journeys. Every point of light above us marks a path that succeeded. A photon left somewhere else in the universe, crossed enormous distances without interruption, and finally reached us. The star we see is not the star itself. It is the final step in that journey. And the darkness around it is not an opposing force. It is simply the vast territory where those paths have not yet crossed our own. If we could somehow pause the universe and look at it from the outside, we might see something extraordinary. Not a static arrangement of stars in blackness, but an immense web of moving light. Photons streaming outward from every star. Photons leaving galaxies in expanding spheres. Ancient radiation drifting from the earliest moments after the universe cooled enough to let light travel freely. Some of those photons would be crossing intergalactic voids millions of light-years wide. Others would be spiraling around black holes, their paths bent by gravity. Still others would be slipping through the thin gas between stars. Everywhere light would be moving, and yet the universe would still appear mostly dark. Because motion alone does not guarantee arrival. Photons spread outward in every direction, thinning as they go. The farther they travel, the less likely they are to intersect with any particular place. So even in a cosmos filled with travelling light, most locations receive only a tiny fraction of it. Which means darkness is not rare. It is the natural state of space. Light is the visitor. Once you see this clearly, the role of stars becomes easier to understand. A star is not just a glowing object floating in space. It is a source, an engine that continuously launches photons into the surrounding universe. Inside a star, nuclear reactions fuse atomic nuclei together, releasing enormous amounts of energy. Some of that energy eventually escapes as light. Every second, the sun releases about 10 to the 45 photons into space. That number is so large it is almost impossible to imagine. But most of those photons will never reach a planet, a telescope, or an eye. They will expand outward into the dark, dispersing across distances so vast that they may travel forever without touching anything at all. And yet a few succeed. A few cross exactly the right path to reach Earth. Those are the ones that illuminate our days and reveal the structure of the sky. This quiet imbalance, billions of photons launched, only a few arriving, is why the universe can be both full of light and still appear overwhelmingly dark. It is not a contradiction. It is geometry. Light spreads. Space is enormous. And our place within that immensity intercepts only a thin slice of the moving photons. The same pattern repeats on larger scales. Galaxies are vast collections of stars, each producing its own expanding spheres of light. When we look at a distant galaxy through a telescope, what we're seeing is the combined arrival of photons from billions of individual stars. But again, the photons we detect are only a tiny sample of the total light being produced. Most of the galaxy's light never comes near us. It spreads into other directions, crossing the cosmic ocean toward unknown destinations, which means that even the brightest galaxy in the sky represents only a small intersection between its light and our location. The rest of its photons disappear into the enormous darkness between galaxies. This also explains why the universe feels quiet. Not in the sense of sound, space carries no sound at all, but in the sense of stillness. Stars burn with incredible energy. Galaxies collide and merge. Black holes consume matter in violent spirals of radiation. Yet from a distance, most of the cosmos remains calm and dark. The activity is there. The light is there. But the distances are so great that only faint traces of those events reach us. The rest of the photons pass silently by. It is a bit like watching fireworks from extremely far away. If the explosions happened miles from where you stood, only a few sparks might reach your field of view. The sky would still appear mostly dark, even though enormous bursts of energy were happening elsewhere. The universe works in much the same way. Countless luminous events are occurring across billions of galaxies, but the photons from those events are spreading outward through vast distances. Only a small fraction arrive here, and that fraction becomes the sky we see, which leads to another realization that feels both humbling and beautiful. The darkness above us is not something separate from the light. It is simply the space between arrivals. Every dark region of sky is a direction where photons are either too sparse, too distant, or still travelling. And every visible object is a place where those journeys finally intersect with us. The sky is not a static painting. It is a constantly updating map of completed paths. Even now, new photons are reaching Earth that have never arrived here before. Some left distant stars when the first animals were just beginning to move onto land. Others departed their galaxies before our solar system even existed. They have been travelling through cosmic darkness ever since. For billions of years they crossed the void between galaxies. They passed through regions where almost no matter exists. They drifted through expanding space, their wavelengths slowly stretching as the universe grew larger. And tonight, some of them are arriving, quietly, unnoticed by most of us. But if one of those photons enters a telescope, or strikes the sensor of a space observatory, a tiny point of light appears where none was visible before. The darkness in that direction gives way. A galaxy is revealed, or a star cluster, or the faint afterglow of an ancient event whose light has been travelling longer than human history. Each arrival expands the visible universe just a little, not by pushing darkness away, but by completing another journey. And when we stand beneath the night sky and allow our eyes to adjust to the faint starlight, we are witnessing only a small fraction of those journeys. Our eyes collect a few photons each second from distant stars, enough to trace out the constellations, enough to see the faint mist of the Milky Way stretching across the sky. But far beyond what we can see with the naked eye lies an even deeper network of light, galaxies too faint for our eyes. Radiation too stretched for human vision. Ancient photons drifting quietly across the cosmos. All of it moving, all of it travelling, all of it part of the slow process by which the universe reveals itself. And in between those arrivals lies the darkness that once seemed so mysterious. Not an object, not a force, just the immense quiet space between journeys of light. A reminder that the universe is far larger than the tiny fraction of it that our eyes happen to intercept tonight. And if we step back for a moment, something even deeper begins to emerge from this quiet picture. Because once we understand that darkness is simply the space between arriving photons, we begin to realize that the universe is not revealed all at once. It unfolds gradually. Light spreads outward from every source, but it spreads slowly compared to the size of the cosmos. Even moving at the fastest speed allowed by nature, photons still need time to cross distance. And distance, in the universe, is enormous beyond anything our everyday intuition prepares us for. So illumination advances slowly. A star ignites somewhere in the galaxy, and its light begins expanding into the surrounding darkness. After 1 year, the expanding shell of light is 1 light-year across. After 1,000 years, it has reached 1,000 light-years away. After 1,000,000 years, that star's photons have begun touching parts of the galaxy that were once completely untouched by its light. But the Milky Way itself is so vast that even after millions of years, most of its regions will never receive that star's light at all. The photons disperse into space, thinning and drifting across distances that stretch far beyond the scale of any single galaxy. This slow outward spread of illumination means that every star quietly reshapes the visible universe around it. Not by pushing darkness aside, but by sending travelers across space. Each photon marks a possible connection between distant places. Most of those connections never complete. But a few do, and wherever they do, a new piece of the universe becomes visible. Now imagine multiplying this process by the hundreds of billions of stars inside our galaxy. Every second, each one is sending out its own expanding sphere of light. Those spheres overlap and cross in complicated ways. Photons from one star intersect with photons from another. Streams of light from distant galaxies pass through the Milky Way as they continue their journeys across intergalactic space. The result is a universe quietly filled with moving light. Not chaotic, not violent, just constant motion in a place so large that most of the motion goes unnoticed. And within that immense web of travelling photons sits our small planet. Earth drifts through the galaxy along with the Sun, orbiting quietly among the stars. From our vantage point, we receive only a thin trickle of the photons moving through the cosmos. Enough to reveal the nearby stars, enough to trace the faint glow of distant galaxies with telescopes, but still only a tiny fraction of the light that actually exists. The rest passes silently by. In this sense, darkness is not really something out there in the universe. It is something that appears because of where we happen to be. If we moved somewhere else in the galaxy, the pattern of visible light would change. Different stars would appear bright, others would vanish from view. Regions that seem dark to us might glow brilliantly from another location. The darkness we see is simply the perspective created by our position within the enormous web of travelling light. And that realization quietly reconnects us with the deeper meaning of the original question. If light has a speed, what about darkness? The question itself turns out to contain a hidden assumption, that darkness must be something moving through space. But darkness never needed to move. It was always there. Everywhere light had not yet arrived. When a lamp turns off, darkness does not flow in. The final photons simply finish their paths. When the sun sets, night does not sweep across the land. Earth rotates away from the stream of arriving sunlight. When a star collapses or fades, darkness does not spread outward. The outward flow of photons simply ends. Again and again, the same pattern appears. Light travels. Darkness remains. And once we see that clearly, the universe begins to feel a little different. The night sky stops being a place filled with mysterious darkness broken by stars. Instead, it becomes a record of journeys completed. Each star is a destination where photons have successfully arrived. Each galaxy is a vast collection of such arrivals, and every dark region between them is simply a direction where the journeys of light have not intersected with us yet. The sky is not filled with darkness that moves. It is filled with distance. Distance across which photons are traveling right now. Distance across which ancient light is still moving toward us after billions of years. Some of those photons began their journey when the universe was young. Some left distant galaxies long before Earth existed. They crossed the enormous voids between galaxies, slipping through regions where almost nothing exists. They passed through expanding space, their wavelengths stretching slowly over cosmic time. And eventually a few of them reached our telescopes. Others reached our eyes. And the darkness in that direction quietly disappeared. Not because it fled, but because light arrived. Yet even now, far beyond the faintest galaxies we can detect, the universe continues. Galaxies still shine there. Stars are still forming. Photons are still leaving those distant places and beginning their long journeys outward. Some of those travelers are already on their way toward our corner of the cosmos. They are crossing distances so vast that their journeys will take millions or billions of years. And for now, until they arrive, the sky in those directions remains dark. Not because darkness is spreading through the universe, but because the photons carrying those distant stories are still traveling, still moving, still crossing the immense quiet between galaxies. And somewhere far out in that darkness tonight, new photons have just begun their journeys. And when we reach that point in the story, the question that started all of this begins to settle into something much simpler. If light has a speed, what about darkness? By now, we can see the quiet answer. Darkness has no speed at all. It does not flow across space. It does not chase light or retreat from it. It never moves from one place to another. Darkness is simply what remains wherever photons are not arriving. Light is the traveller. Darkness is the background. And once you see that clearly, the universe begins to feel less like a struggle between brightness and shadow, and more like a vast landscape slowly revealed by moving light. Stars ignite and send photons outward. Galaxies glow and scatter ancient radiation across intergalactic space. Supernovae erupt, launching waves of light that cross the cosmos for thousands or millions of years. Some of those photons succeed in reaching distant worlds. Most do not. But every time a photon arrives somewhere new, a small patch of the universe becomes visible. And that process has been unfolding since the early moments of cosmic history. For billions of years, photons have been crossing the darkness between galaxies. They slip through immense voids where almost nothing exists. They bend around massive objects. They scatter from dust and gas. They stretch as space itself expands. Yet they keep moving, second after second, year after year, for spans of time longer than human history. And every so often, one of those travellers reaches its destination. A detector inside a telescope registers its arrival. A faint point of light appears in an image. A new galaxy becomes visible where there had once seemed to be nothing at all. That moment is not the birth of the light. It is the end of a journey. Somewhere far away, long ago, the photon began moving outward through space. It crossed enormous distances without ever slowing down. It passed through darkness that never moved. And at last, it arrived. This is how the visible universe grows. Not by pushing darkness away, but by completing journeys of light. Every telescope on Earth participates in that quiet expansion of awareness. Astronomers aim their instruments toward regions that appear empty and simply wait. They collect photons slowly, minute after minute, hour after hour, and gradually, the darkness begins to reveal faint structures, galaxies so distant that their light began travelling billions of years ago. The deeper the observation, the more photons arrive, and the more arrivals we collect, the more the universe unfolds. Yet even with our most powerful telescopes, most of the cosmos remains unseen. Beyond the farthest galaxies we can detect lies an even larger expanse of reality. Galaxies still shine there, stars still burn, photons are still leaving those distant places right now, but their journeys toward us are only beginning. Some will take billions of years before reaching this small planet. Others will never arrive at all, carried away by the expansion of space. For us, those places remain dark, not because darkness fills them, but because the light has not reached us yet. And perhaps that is the quiet beauty hidden inside the question we began with. The darkness above us is not empty. It is simply unfinished. Every dark patch of sky is a direction where photons are still travelling across the immense distances of the universe. Some are already halfway here. Some have just begun their journey from distant stars. Some may still be crossing the vast spaces between galaxies long after our own civilization has passed into history. And one day, perhaps millions or billions of years from now, a few of those travellers will finally arrive somewhere. A telescope will detect them. An observer will see a faint new glow in the sky. And in that moment, the darkness in that direction will quietly disappear. Not because darkness moved away, but because light finally arrived, which means that every time we look up at the night sky, we are witnessing something extraordinary. We are standing at a tiny intersection point in the universe, a place where journeys of light from unimaginable distances finally end. The stars we see are not just objects. They are arrivals. They are photons that crossed years, centuries, or millennia to reach us. The faint galaxies and deep images are even older arrivals, carrying messages from epochs when the universe itself was young. And the darkness between them is not something advancing through space. It is simply the immense quiet waiting between those arrivals. Light travels, darkness waits, and somewhere, far beyond the faintest glow visible tonight, countless photons are already moving through that quiet. They are crossing the deep spaces between galaxies. They are drifting through the silent voids where almost nothing exists. They are moving steadily, second after second, at the fastest speed nature allows. For now, we cannot see them. Their journeys are still incomplete. But one day, somewhere, those travellers will arrive. And when they do, another tiny piece of the universe will step out of the darkness and into the light.